So welcome back to Physics 221. This is chapter 36. This is about special relativity. This is something that Einstein developed. Now, before we get into anything, I want to explain special. So special, it just means restricted. So special relativity only deals with unaccelerated motion. So you want to always keep that in the back of your head, all right? Unaccelerated motion, so constant velocity. So we're going to talk about reference frames, and we're going to talk about inertial reference frames, which we learned in Physics 121. Inertial reference frames like a jet or a train, you know, your reference frame or a car, has to be non-accelerated, so the velocity is constant. So keep that in the head. Okay, so that's what special means. After Einstein figured out special relativity, then he took the more general case, and it's called general relativity. We won't talk about that. Sorry. All right. We're going to understand and reason with the fundamental concepts of event and reference frame. We're going to understand how the principle of relativity leads to the relativity of simultaneity and length, and thus to time dilation and length contraction. We'll use the Lorentz transformations of position and velocity. We'll explore relativistic energy and momentum, and we'll learn about E equals mc squared. Now, you're going to see that relativity, the mathematics of relativity is not so bad, but getting the conceptual understanding is really challenging because we're going to learn things that completely disagree with our everyday experience, our common sense. So it's not easy, so just be aware of that. All right, so I apologize, but I was not able to get this thing to work. So this is just a couple of minute long video clip. It's awesome. So if you would, just pause your video and watch this little video clip. Just like the first couple minutes, until the little girl is, well, I don't want to give it all away. Just the first couple minutes. It's just terrific. Okay, before we get into relativity, I'm going to give a brief, maybe not so brief. I'm going to give a sort of brief history lesson. And I promise you, we're going to talk about most of this again in gory detail. But I just kind of want to give you this little history lesson. So basically, you know, I always wondered what led Einstein to come up with this? You know, I mean, he pretty much did it all by himself. So what led Einstein to develop these principles of special relativity? Oh, yeah, you're supposed to. That's what they say in the video at the very end of the first couple of minutes. So you're supposed to watch until till the narrator says that. All right, so here we go. So yeah, we're going to talk a lot about Physics 121 in this chapter. Okay, so there's the man, right? So in Physics 121, we learned about something called the Principle of Relativity. And they knew this at the time of Galileo and later Newton and all that. So the Principle of Relativity says the laws of physics are the same in all inertial reference frames. Well, no kidding. I mean, we still believe that. What does that basically say? It basically says if you did an experiment here in this room, and then you did the same experiment in like a train, constant velocity, or you did it in a jet, constant velocity, you get the same results. Okay, doesn't that agree with your experience? Yeah. I mean, no kidding, right? All right, so they knew this at the time of Galileo, and we still believe it is true. Now, Galileo, okay, this is 121. We've got to understand this. So Galileo, he worked out all of the equations, but let's get back. So here are two reference frames. So this could be, the room, S. This could be, a jet, S prime. Well, we don't care. We don't know. Here's the important thing. All we want to know is that S prime, the S prime reference frame, moves with velocity v relative to this reference frame. Now, don't get caught. We know nothing about this reference frame. It doesn't have to be at rest. This could be a jet. This could be a different jet that's moving relative to this jet. We don't know. All we're saying is that S prime reference frame is moving relative to the S reference frame with velocity v. That's all. Okay, so inertial reference frames, velocity is constant, no acceleration. Okay, that's all. Big deal. All right. So here's the notation. So let's say we have a particle. Okay. So the velocity of the particle is moving. So the velocity of this particle, we're going to say it's v in the s frame. And we're going to say it's v prime in the s prime frame. Okay. Big deal. Okay. So Galileo worked this all out. And what he figured out was that the velocity of the particle in the s frame was equal to the velocity of the particle in the s prime frame plus the speed of the s prime frame. Okay, now, this is so logical. Here, let's do it. Let's just say that s prime, no, let's say s is the ground. All right, so we're outside, we're outside just sitting down, wasting time. And that's our reference frame, right? The earth, the ground is our reference frame. And then let's say that s prime is a moving car. Right, moving car. And then let's say that somebody stands up in a car, no air resistance, of course, and there's no roof on the car, convertible car. So somebody stands up on the roof and throws a ball. Okay? So the question is, what is the speed of the ball relative to us on the ground? Well, come on, this is a piece of cake. So, okay, let's say that the velocity of the car relative to us, right, relative to the ground, let's say 60 miles an hour. 60 miles per hour. And let's say that the velocity of the baseball, ball, relative to the moving car, let's say it's 100. All right, it's really a really good picture, okay? All right, so this is the velocity of the ball relative to the moving car. Well, what are we going to measure? What's going to be the velocity of the ball relative to us, relative to the ground? Well, come on, it's simple, right? You just add them. So it's going to be 160. So that kind of makes sense and agrees with the data, and we don't have a big problem with it. By the way, there's a really cool YouTube video. You should look for it. And they have it. It's not just on YouTube. There's another one somewhere else too. It's Japanese, but they have a truck moving this way. Let me just make up 100 kilometers per hour. I don't remember, but a truck moving this way at 100 kilometers per hour, and then they have a machine on it that shoots a baseball at 100 kilometers per hour. So what's somebody on the ground going to see? Just fall straight, right? So they actually have a video of that, and then they do it in slow motion, and it's awesome. The ball just goes straight down, Okay, so all I'm saying is, no kidding, common sense, I mean, whoopee. That's not a big surprise. Okay, so anyway, so Galileo, he worked out, this is called the addition of velocities equation for obvious reasons. Okay, now he also worked out the other equations. So notice, these reference frames are just moving in the x direction. Keep it simple. And so the z is the same, the y's are the same. Okay, this is the same thing as what we just said. Okay, x prime equals x minus vt. Why is that true? Well, remember, let's see. What's this distance right here? It's that, right? So isn't this distance equal to this distance minus that? Right? That's a stupid way to write it. Let's just say, well, maybe not. Let's just say, let's go with this. X prime plus vt equals x. So x prime is this, x prime is this, vt is this, and that's just equal to x, right? That's equal to position in this reference frame. Okay. So anyway, Galileo worked these things out, and everybody believed them, and everybody was happy, and they agreed with the data, and everything was just wonderful, okay? Wonderful. All right. Now remember, Galileo, when he was alive, and Newton, physics was just like mechanics. No one had come up with a theory of electricity and magnetism yet. Okay, so much, much later, in the 1860s, there's a guy named Maxwell. And these are supposed to be like that. Don't worry about it. All right, so in the 1860s, there was a guy named Maxwell, and he studied all of the experimental evidence and data dealing with electricity and magnetism, and he decided to write the mathematical theory. And you always want to have a mathematical theory because you want to explain things and also predict new phenomena. So Maxwell, he actually had a whole lot more equations than this, but don't worry about it. But anyway, so these are Maxwell's equations, and they explain everything there is to know about classical electricity and magnetism. So they agree with the data. They're awesome. Okay, they're totally, totally awesome. Physics 220 is basically learning what these equations mean, believe it or not. Okay, so this was totally wonderful. This was like a huge intellectual achievement. Except there was one problem. Maxwell's theory did not agree with the principle of relativity. Okay? So at the time of Maxwell, this is what the principle of relativity said. The principle of relativity, the laws of physics, mechanics, but not electricity and magnetism are the same in all inertial reference frames. Now when you think about it, that's totally insane. I mean, think about it. When you go up on an airplane, does your flashlight work the same as it does here on Earth? Yeah. Does your computer work the same as it does on Earth? Yeah. I mean, come on. You know, the same laws of electricity and magnetism work on the airplane than they do on the Earth, you know. So this is totally ridiculous. It's totally ridiculous. Okay? So, something is wrong, all right? Something is wrong. Okay, Einstein thought a whole lot about this. He was a theoretical physicist, by the way. So Einstein thought a lot about this. And he basically said, he just felt strongly that Maxwell's equations should agree with the principle of relativity. Okay? I mean, why not? You know, they should. I mean, all the evidence points to the fact that they should. And this is like, principle of relativity is so fundamental, you know? So he just said, look, electricity and magnetism have to agree with principle of relativity. All right. So he said, well, you know, maybe they do. But maybe the problem is with the Galilean transformation equations. You know, maybe this is what's wrong. And maybe this is wrong. Now that was a really bold step because there had been, I mean, what are you crazy? This had always worked, you know. The velocity equation agreed with the data. This agreed with the data. I mean, what do you mean these equations are wrong? Well, that's what Einstein said. He said, look, the only way, I mean, electricity and magnetism should agree with principle of relativity. So the problem has to be with the transformation equations that Galileo came up with. All right. So what did he do? Well, he's a theoretical physicist. What do? You come up with your own transformation equations. So he came up with his own transformation equations. And these transformation equations work for mechanics, right, and electromagnetism, electricity and magnetism. So it was incredible success, right? But what's funny about this thing is that there was a guy named Lorentz who had already figured these equations out. But Lorentz never took the next steps to see what they kind of imply, you know? He figured out these equations and he really didn't know what to do with them, so he stopped. Bummer. So Einstein independently figured them out, and then later on realized that Lorentz had already done it. So most people just call them the Lorentz transformation. Some people try to be nice, and they call them Lorentz-Einstein transformation equations. But, you know, Lorentz did it first, so he gets the glory, you know? Okay, now, there's a price to pay. There's a price to pay. So you notice here, you know, the time in the S frame equals the time in S prime frame, right? Time is time, come on. But what do the Lorentz equations say? Oh my gosh, the times are different. The times are different. Okay, so basically, when Einstein or Lorentz came up with these equations, and Einstein recognized this, Lorentz didn't. Einstein recognized, oh my goodness, if these are true, which they appear to be true because they work with the mechanics and electrodynamics, if these are true, there's a huge price we got to pay. And Einstein, he was willing to do it, whereas Lorentz was clueless. He had no idea. All right. So here is what, and we're going to learn about this in gory detail, right? So this is what Einstein realized. He realized that if these equations are true, which they appear to be, therefore time is relative. What does that mean? Well, is this large or small? Well, it's large compared to an atom, but it's small compared to Saturn. So, size is relative, right? There's no such thing as absolute size. So these equations show that time is relative. There's no such thing as absolute time. Whoa! So what am I talking about? So let's say I'm running. Let's say you're stationary and I'm running, and I sneeze. So let's say that you measure the duration of my sneeze, and I measure the duration of my sneeze. And our equipment is perfect. If I'm running relative to you, we're going to get different answers. And you're right, and I'm right. That's weird, right? So that's what it means. Time is relative. There's no such thing as absolute time. These equations also predict that space is relative. There's no such thing as absolute space. What are you talking about? So let's say I have a meter stick here. So I'm running relative to you. You're stationary. I'm running relative to you. And we measure the length of the meter stick. I'm going to get 1 meter. You're going to get something different. And we're both right. So that's weird. Okay? The velocity equation, the velocity addition equation that we talked about earlier, the baseball and the car and all that, it's wrong. Okay, simultaneity, two things happen at the same time. Simultaneity is relative. There's no such thing as absolute simultaneity. It depends on your reference frame. So if you have two reference frames, one is moving relative to the other one, something might be simultaneous in one, but not in the other. And mass is equivalent to energy. That's E equals mc squared. Wow! So this is mind-boggling, right? Completely mind-boggling. Okay, so that is the end of the brief. Didn't turn out to be brief. That's the end of the brief history lesson. So now what we have to do is we have to go through that in gory detail. Okay, so we're going to do some Physics 121 first. So we're going to talk about reference frames. Okay, so am I moving? So pause your video and answer it. Okay. Meaningless question. Why? Well, hopefully I wasn't moving relative to this room, but is the Earth moving relative to the sun? Certainly. So was I moving relative to the sun? Certainly. So that's what I mean. It's a meaningless question, right? Okay, you're driving to town on H1. The speedometer in your car reads 45 miles an hour. People like you drive me crazy. I am also driving to town on the same section of H1, and since you are driving so slowly, I pass you. The speedometer in my car reads 60 miles an hour. What is my real speed? Now, if you look at this picture carefully, you realize it's really not H1, right? Because this is kilometers per hour. But I couldn't find a picture of H1 on Google Images, so this is the best I could do. All right, what is my real speed? So pause your video and figure it out. It's a meaningless question. Why is it a meaningless question? Well, because objects move relative to a reference frame, okay? So somebody on the ground is going to say I'm doing 60. What you're going to say, okay, relative to you, slowpoke, I'm doing 15. What am I doing relative to me? I'm not moving relative to myself. That's kind of weird, right? So the velocity of me relative to myself is 0. So all I'm saying is that objects move relative to a reference frame. If you're going to ask a question like that, what's my real speed? You have to say, relative to the ground, relative to the moving car. You got to say something. You can't just say, what's my real speed? Okay. You and your friend are comfortably seated on the French TGV, that's that super fast train, as it moves quietly along the tracks towards Geneva, Switzerland at 300 kilometers per hour. Just before you both fall asleep, another TGV going in the opposite direction passes your train on nearby parallel tracks. Will you and your friend agree or disagree concerning the speed of the other train? So pause your video and figure it out. Okay, the answer is you will agree. Why will you agree? Because you are both in the same reference frame, right? You're both sitting down on the first train, and so you're in the same reference frame. On the other hand, you and your friend are comfortably seated on the French TGV as it moves quietly along the tracks through Geneva, Switzerland at 300 kilometers per hour. Your type A friend decides it's time for a run and begins a sprint down the aisle. When she is sprinting away from you, another TGV going in the opposite direction passes your train on nearby parallel tracks. Will you and your friend agree or disagree concerning the speed of the other train? Now this is, you're not allowed to do any calculations or anything like this. It's just what you notice, okay? Well, so pause and figure it out. Okay, hopefully you'll agree, disagree, right? Because now you're in different reference frames. You're in different reference frames. So you're going to get different answers. Okay? So here we go. Let's summarize. Objects move relative to a reference frame. All experimenters at rest relative to each other share the same reference frame. So they're going to get the same measurements. Experimenters moving relative to each other, like you and your type A friend, do not share the same reference frames. So you're going to get different measurements. Okay, this is still Physics 121. You are running okay, let's see, this is you. You are running forward at 10 meters per second. You're pretty fast. Relative to the ground. A person standing still behind you throws ball A horizontally towards you at 30 meters per second. A person standing still in front of you throws ball B horizontally towards you at 30 meters per second. Another person sitting still in front of you throws ball C straight up in the air at 30 meters per second. What are the speeds, not velocities, the speeds. What are the speeds of balls A, B, and C relative to you? Now, please just think about it. No equations, all right? I know we learned how to do this with equations in 121. Don't. Just think about it. So pause and figure it out. Okay, we're back. All right, so you're going at 10. The ball's going at 30, same direction. So obviously, you're going to think this thing is going 20. Agree? All right, so velocity or speed of A relative to you is going to be 20 meters per second. Okay, let's do B. Now this one's 30 this way, but you're going 10 that way. So what's it going to be? 40. Right? 40. Just a speed, okay? Just a speed. I mean, the velocity would be this way, right? But just a speed. So B relative to you, just a speed, is 40 meters per second. Okay, now what's this crazy thing going to do? Well, it's Pythagorean Theorem, right? So velocity of C relative to you. Okay, so there's going to be the 10 horizontally and the 30 vertically. So it's going to be 10 meters per second squared plus 30 meters per second squared, square root of 31.6 meters per second. All right, so that should hopefully make a lot of sense since we talked about it in Physics 121. Okay, now remember this crazy equation? So A is on the left, A is on the left, B is on the right, B is on the right. These guys cancel. Right? That was that funny equation that we learned. Okay, now please use this equation and figure out this. So pause your video and figure that out, please. All right, let's do it. So VAY, right? VAY equals VA ground plus V, right? VA ground plus V ground U, right? A is on the left, A is on the left. Y is on the right, Y is on the right. These guys cancel. Okay, what's VA ground? 30I. I'm not going to write units, sorry. 30I. And what's V ground U? Now look at VU ground is that way. But what's the velocity of the ground relative to U? It's that way. Remember doing that? So it's minus 10I, which is 20I. So the speed is just 20. All right? Let's do VB. VBY equals VB ground plus V ground U, right? Okay, so what's the velocity of B relative to the ground? Minus 30, minus 30I. What's the velocity of the ground relative to U? Minus 10. So we get minus 40I. So the speed is 40, which is what we had. Let's do the last one, the C. Okay, VCU equals VC ground plus, why do I keep doing that? Plus V ground U, right? Okay, so let's see, VC ground. Okay, what's VC ground? Just 30 that, right? 30 that way. So it's 30J, right? J is, okay. And what's V ground U? V ground U is minus 10. Minus 10I. So, so therefore what's the speed? It's that, right? It's the same thing. Okay, so that's like a review, just make sure you can do it. Okay, we got to keep doing Physics 121. I already explained that, right? But let's just keep going. So the axes of S and S prime have the same orientation, so we're only going to be moving in the x direction, keep things simple. So the y's and the z's are going to be the same. At time equals 0, the origins are going to be the same, right? So that's nice. Okay, so both origins are on top of each other, whatever, the same at time equals 0. And in this reference frame, like a train or a car, moves to the right with velocity v. And I'm sorry, I noticed that sometimes Randy Knight uses uppercase v, sometimes he uses lowercase v. He's not really consistent. Sorry about that. And again, we know nothing about S. So don't always assume this is at rest. All we know is that this reference frame is moving to the right relative to this reference frame with speed v. That's all we know. Okay. All right, so here we have two reference frames, right? S and S prime. And again, S prime is moving relative to S. What are the Firecrackers' coordinates in the S prime reference frame? Well, that's sort of obvious. Agree? Just X prime, Y prime. So, no kidding. Okay, no kidding. Now, here's a tough one. Okay, what are the Firecrackers' coordinates in the S reference frame? So please, honestly, pause your video and figure this out. And I gave you some hints, right? Remember, the origins coincide to equal 0, and this guy is moving with velocity v relative to this guy, right? And it only moves for a time t. Okay, so how far has this reference frame moved? Well, distance equals speed times time, right? So S prime has moved this distance, right? This distance, right? Okay, so what are the coordinates according to this guy? Well, this distance is the VT. This distance is the X prime. So therefore, we're going to say that X prime equals VT, X equals VT plus X prime. Right? Right. So there's VT, so there's X. So X equals VT plus X prime. Okay, awesome. That makes good sense. All right, so, and we don't worry about Z. Okay, now again, these are the Galilean relativity equations, which we know are wrong, right? Einstein showed they're wrong. But it's good to review them, all right? Because actually, they're okay unless the velocity of the reference frames is near the speed of light. But we'll get to that. Okay, so these are the, the position transformation equations. So how do you get, I want to get the velocity transformation equations. So if you have the position transformation equations, how do you get the velocity transformation equations? Well, in Physics 121, where we know calculus, we can answer that question, right? You just take the time derivative, right? So we have x equals vt plus x prime. And we take the time derivative. So we're going to have dx dt equals, oh man. Okay. All right, so take the derivative. Dx dt equals v plus dx prime dt, right? Okay, I mean, that's it. Yeah? Okay. All right, so there it is, right? Okay, so I'm sorry. So there's the velocity. So here are the velocity transformation equations. Now, rainy night's on a rotten thing. Okay, so what is dx dt? That's the velocity of the particle in the S frame. Randy Knight is going to call that u. So he's reserving the v for the speed of this S prime reference frame, the speed of the car or the train. Okay, sorry. All right? So all I'm saying is this is going to be u equals v plus u prime. Okay? Whoopee! That's what we get here. All right? U equals u prime plus v. Okay, why? Whoopee. All right, okay, that's all. All right. That's all there is to it. Again, these are the Galilean relativity equations. All right? Now, more Physics 121. We studied elastic head-on collisions in Physics 121. And this is what we said. We said, imagine you have a ball, m1, speed v, 1 initial, colliding with this guy at rest. Different ball. What's going to be the final velocities of each ball? So what we did, we actually didn't do it, but what you could do, they did it in the book, you conserve, this is an elastic, so the kinetic energy is conserved. It's a collision, there's no external forces, so the momentum is conserved. So you could write the kinetic energy conservation equation, the momentum conservation equation, and do a ton of algebra, and you come up with this. And we went through this in gory detail. I hope you remember. All right, so that's great. So it gives us the final velocity of this guy and the final velocity of this guy, because that's what we wanted. All right, now, but again, we only did this for this ball at rest. So here's a question for you. We have these wonderful equations when m2 is at rest, but now I have a situation where m1 is moving at 50 meters per second and v2 is not at rest. It's moving at 20 meters per second. Well, I don't feel like writing conservation of kinetic energy, conservation of momentum, doing a whole bunch of algebra. I want to be smart. I just want to use these equations. So how can I do that? What's the only difference? Well, obviously, this guy is moving, whereas this one is not. So what can I do? So pause your video. All right, come back. All right, so we're back. So what can we do if we want to use these equations but we want to solve this problem? Well, I hope you realize that it's a total piece of cake, right? All we have to do is pretend that we are running, oh boy, that's kind of crazy. We're on a bike at 20 meters per second, okay? So if we're going this way at 20 meters per second, what's the velocity of this guy? 0. What's the velocity of this guy? 30. So then, right? So then we have this, right? We'll say this is 30, this is 0. We plug everything in. We'll get some velocities. That's what we got to do. Then we just have to add 20. Big deal, right? So that's why this is kind of a really wonderful equation, because we can use it for lots of things. Okay, so yeah. So this is just what I talked about, okay? So just read that on your own. These are the equations. And he uses U's and all that good stuff. So make sure you read that and understand it. It's just review, you know. Okay. All right, now here's a cool question. Okay, if you know who Bill Russell is, you get an A for the class. So I grew up in Boston. Well, I was born in Boston. I grew up in New Hampshire. And the Celtics were the team. They would always beat the Lakers. And Bill Russell was the center. He was like the superstar of the Boston Celtics. But anyway, here's the question. You ate Wheaties for breakfast today, cereal. A lot of Wheaties. You are late for class, so you're running forward at 100,000 kilometers per second relative to the ground. That's impossible. Who cares? A person standing behind you shoots a light wave toward you at 300,000 kilometers per second. That's the speed of light. A person standing in front of you shoots a light ray towards you at 300,000 kilometers per second. Now, here's the important part. According to Galilean relativity, at what speed do the light waves approach you? Okay. So let's do it. Okay, so you are going at 100,000 kilometers per second. And then somebody behind us shoots a light wave, 300,000 kilometers per second. And then somebody in front of us shoots a light wave. All right. According to Galilean relativity, work it out. So pause your video and figure it out. Okay, so we're back. All right, so what would you, according to Galileo's equations, what would you measure for this guy? Well, this is 300,000, but you're moving 200,000. So you would measure 200,000, right? Okay. You're going this way, this guy's coming that way, so you add them. So for this guy, you'd measure 400,000. Right? That's what Galilean relativity would predict. Makes pretty good sense, right? Just add velocities, add and subtract velocities. Okay, now here's the fun part. If we, oh, you didn't see that. No, don't do that. Hold on. I guess I got to quit pretty soon. Okay. Now, if you actually did the experiment, this is what's fun. If you actually did the experiment, you would not get this. You would not get this. You would get 300,000 kilometers per second. Now, if that doesn't surprise you, either you already know about relativity or you're not paying attention. All right, this is shocking. Because what does it mean? It means that the speed of your speed is irrelevant, right? I mean, it's crazy. It just means that light travels at the same speed no matter how fast the guy holding the flashlight is going, no matter how fast you're going. It just means that everybody measures the speed of light to be the same, which is completely wacko, right? Completely wacko. Because again, think about it. If you're in a rocket ship, and the rocket ship is going half the speed of light, and the rocket ship turns on the light beam, Galileo would say the light beam is going speed of the rocket plus speed of the light, which is 1.5 times speed of light. Experiment disagrees with that. Experiment shows that everybody measures the speed of light to be the speed of light. Simple as that. End of discussion. Okay, that's a good place to quit.